Hi everyone, and welcome to another episode of an OWASP Switzerland meeting. Today with me here from OWASP Switzerland is Paddy and myself, and of course our speaker Petar. Before we start the presentation, just very few information. So for those that might not know OWASP that well, you can become a member. So if you enjoyed today's presentation, you're very, very welcome to become a member. There are like some perks, like you get discounts on, for example, the conference entries. You get, for example, free trainings that you can do online. So a lot of things. I would highly recommend it, and you definitely support the cause of OWASP, of making application security more visible if you become a member, be it yourself or also your organization. Then also, we're also always looking for you. Yes, you as the speakers. So if you think you're one of those few unicorns out there that could help us out and have something great to talk about, please reach out to us. And we are more than happy to offer you a slot to show like your tool, some project that you work on, or just the general concept, as long as it's somewhere around the topic of application security or security in general. So what will be happening today? So first, the introduction I'm doing right now. Then we will have very interesting talk today about quantum computing and the effects it has on cryptography. There, just enjoy, lay back, but also feel free to add your questions. You can give us your questions either through the YouTube channel directly if you want to, but we have a lot of people joining in that want to stay anonymous. That's totally fine, of course, for us. I will show you in a second how you can then stay anonymous and still ask your questions. We have a specific platform for that. Regarding that question, or regarding question in general, we will answer questions in the end. So please stay tuned. We will put them together and ask Petar as our speaker all of the questions at the end. And after that, we will be done for the day up to or waiting for our next meeting. So for those Q&As that you want to have anonymously, we have on owasp-switzerland.ch, we have a very small, very simplified platform. You can have your name entered there, but you can also post anonymous questions. And as said, we will answer them at the end of Petar's talk. And by that, nothing else. So I welcome Petar. Petar Bersic is today talking about quantum computing and its effects about cryptography. And I'm sure Petar will also just say a few words about himself. So thanks for being here, Petar. The stage is yours.
Thank you. Welcome to this talk about quantum computing and cryptography. My name is Petar Bersic. I work as a DevOps engineer at Sulca, and also I study for in a master's program in quantum engineering at ETH. So our talk today, our topic is the quantum computing and cryptography. And the first thing we need to understand about this is the concept of a state in physics. So in physics, we study, the thing we study, we call a system. Everything outside of that system, we call the environment. And the important thing about a system is that it has a state. At a certain point in time, a system has a state. And this state is some object that we define and that holds all the information that can be known about this state at some point in time. And now, quantum states, unlike classical states, a quantum state can also be discrete. An example of a continuous quantum system would be a free particle with its position and momentum. Such a particle doesn't have a quantized energy levels. It can have whatever energy it wants to have. But in quantum mechanics, we have these discrete quantum systems, such as, for instance, the harmonic oscillator, or an energy states of an electron in an atom, like here, down here, we have a hydrogen atom, and the electron on the hydrogen atom comes in certain states, certain energy levels, and they are discrete. Here on the left, we have an example of a harmonic oscillator. A harmonic oscillator is, for instance, such a pendulum, and the energy of such a pendulum is quantized, meaning that it can only come in these quantities. So it has the ground energy, and then it has the harmonic oscillator has a fixed frequency. And then there's this Planck's constant, which gives you the multiple of this, gives you an energy step. Now, total energy of a harmonic oscillator comes in these different steps, which are quantized. And the important thing here is that energy of a harmonic oscillator cannot come on this level or this level. It must come in these steps. And this brings us to the concept of a quantum state. Again, a state is an object that holds all the information that can be known about a system. And a quantum state has some states which are incompatible with each other. We call these the base states. And mathematically, we associate with each quantum state a vector in a set, and this set is called a Hilbert space. Now, vectors in quantum mechanics, we have decided to mark them like this. So this inside of these, this is called a ket. Inside of the ket is just, everything inside is actually a name of the vector. It has no more meaning than that. So this vector is called 0, this vector is called dead, this vector is called alive, and this vector is called higher energy state. Now, quantum states can build superpositions. What does this mean? Well, suppose you have a ball on a staircase. Now, this ball can have, when you perform a measurement, this staircase represents energy levels. So when you ask a system, what is your energy level? It will always be one of these. So 0, 1, 2, 3, 4, and so on. But what quantum mechanics tells you is that if these are possible states, these distinguishable states, then a linear combination is also a possible state. Now, a linear combination just means you add some complex number times this vector plus some other complex number times this vector, and so on. And this is called a superposition. Now, how you interpret this is up for debate, but the way you can imagine it, like I've drawn here, is that instead of having a ball at a specific point, you actually have the ball distributed across all of these different levels. In a sense, it is in all of these levels at the same time. The interpretation is not so important. Mathematically, it works. What it actually means is not completely clear, but it still works just the same. Now, we will focus on this talk on a two-level system. A two-level system is known also as a qubit. So we will ignore any higher energy levels and only focus on systems that have two energy levels. And these things are called qubits. Now, I promise there will not be a lot of mathematics in this talk. Here is an exception because I really want to demonstrate how this works. So we have an initial state, which is, as I've said, a linear superposition of 0 and 1. Now, if you remember your vectors from school, what this is, the 0 and 1 vector, they are actually just orthogonal, meaning they are at the right angle to each other. And every other vector can be expressed as some number times this plus some number times this. This is what we did here. Now, there is a constraint in quantum mechanics that says that these vectors, because they actually represent probabilities, they have to be of length 1. And because of that, we have only two real parameters to fully specify the state of a qubit. So here, intuitively, we would imagine alpha is a complex number, meaning it consists of two real numbers, and beta consists of two real numbers. So we would have 4 real numbers to describe a state of a qubit. But in reality, because of this condition, we constrain one parameter, and because of another condition here, which is that the global phase is irrelevant, we can ignore it. This is just a mathematical artifact. what you can express this general state here as this. And this has only two real numbers. It has the theta and the phi, the two angles. And this then brings us or allows us to visualize a qubit. So again, what we are just doing, we are visualizing this sum, but we are visualizing it. We have rewritten this sum in this way and assigned these two numbers with it. And what this allows us to do is to make a visualization called the Bloch sphere. Now, a Bloch sphere just means, so we have rewritten, as I've shown in the last slide, this up here into this. And now, every state of a two-level system can be shown as a point on this sphere. So the angle, where the angle between the z-axis and the state of the system is theta, and the angle between the x-axis and the projection of this state onto the xy plane is this psi, which means that these two things just give you any point on this sphere. On the right is a sphere that we will use more often during this talk. It is exactly the same thing as the left. The red vector is the 0 state, the green vector is the 1 state. And then these four vectors are just four examples. It can be anywhere else on this sphere can be a state of our two-level system. Now, we now have a single qubit, but a single qubit is not really all that useful. It's only one qubit. We need a way to build states with multiple qubits. And the way we do this mathematically is with something called a tensor product. Now, a tensor product here is marked with an arrow. What it means is if we have a qubit 1 in the state psi1, a qubit 2 in the state psi2, the compound system, the combined system of the two is going to be this tensor product. Specifics of mathematical specifics are not so important, but the point is that we now have a state which has the 0, 0, 0, 1, 1, 0, and 1, 1 component. Now, these are base vectors. These are incompatible with each other, just like those 0, 1, 2, 3 levels were. And when you measure, you will fall into one of these vectors. And these numbers in the front represent amplitudes, or we will see. These numbers in the front have a specific meaning. Okay, and their meaning is related to the measurement. The first thing is to choose a basis. What this means is you choose if you want to, in our case, we always choose the 0, 1 basis. So what does the measurement in quantum mechanics do? So it takes, suppose you have a two-level system like here on the left, which is a superposition or some sort of distribution between 0 and 1, and described schematically as this kind of cloud or delocalized. So that, like the ball is here and here at the same time. When you perform a measurement, this means you interact with this system somehow. In most cases, what this means is shoot a laser at something, or you play a microwave, play a microwave signal to something, and this forces that two-level system that you have into one of these states. So it either goes into 1 or it goes into 0. Which one, you don't know. What you do know is you know this state before you have measured it, and this is a postulate of quantum mechanics that if you take this number in the front, take the absolute value and square it, this is the probability that you will get this result. It seems a bit random. You take absolute value of this and you square it, and that's what gives you probability. But that is what quantum mechanics says we should do, and that is what we do. Now, a state, if it just existed as a point on the sphere, would be, again, not very useful. We need to be able to control where this state points to. We need to be able to control where this vector on this sphere is. And the way we do this, we have two control parameters, essentially. We have the initial state. We can initialize the vector to be somewhere. Most often than not, we initialize it to be in 0. And this has to do with how these two-level systems are usually physically achieved. And the easiest thing to do is just to cool them down until they reach 0. And then once you have the initial state, you have to control it with this other pre-parameter, which is called the Hamiltonian. Now, the Hamiltonian is actually, it's a matrix, but what it actually represents is the energy to the system. So when you shoot something with a laser, you give it a non-zero Hamiltonian. When you play a microwave frequency for a different system, you give it a non-zero Hamiltonian. Now, what this on the left is a differential equation, but on the right is actually the consequence of that equation. What this tells you is that because we have said states have to be of length 1, they cannot reduce or increase in length. This means that this matrix in front of it, what this tells you is that a state at any point in time, later point in time, is the initial state multiplied by this matrix U. Now, this matrix U must be special in the sense that it must not change the length of any vector that you give it here. And matrices that don't change the length, that just rotate the initial vector, are called unitary matrices. And so quantum mechanics, the time revolution in quantum mechanics is unitary for this reason, because the state may only be rotated. And the only matrices that do that are the unitary matrices. Now, here is then the general kind of idea. You initialize the qubit in a state 0. You apply you give it some energy with this Hamiltonian, which then gives it some U over some time. And then you get a superposition between 0 and 1. And then when you make a measurement, you either get a 0 or get a 1 with this absolute value of the first one squared, or this one absolute value of the second one squared. And now, an important thing to realize about quantum states, and I would say probably conceptually one of the most important things to realize, is that they are different from probability mixture. What does probability mixture mean? It means that suppose you have a black box and you put in something that is 50% 0 and 50% 1. When you make a measurement, of course, you will get a 50% 0 and 50% 1. But a quantum state is a bit different. If you put a system into this superposition where it is equally in 0 and equally in 1, and with our rule, square root of the absolute value of this squared will give you 1/2 or 50%. In this case, it would appear that the quantum state after the measurement is the same thing as if you only initially had something 50% in 0 and something 50% in 1 state. But this is not so. Why? Because what we can do using those H parameter, we can rotate a state we have inside. So suppose we have this state, and now we apply a Y rotation. So what does this do? So if Y is the axis of rotation, and pi half means a quarter turn, what does this do? This state actually on the block sphere is here. When you apply a rotation over this y-axis, this rotates down into 1. But what happens to these ones? 0 rotates here, and 1 rotates up there. Both are on the equator, which means any state that is on the equator, when measured in this 0, 1, will give you 50%. 50% go up or 50% go down. So now, suppose you had a black box. In one black box, I put a quantum state like this, and in another black box, I tell you there is 50% chance I put a 0 or a 50% chance I put a 1. What you do is, to figure out which one it is, you would need many boxes, but what you do is, you apply a pulse, which gives it, you connect a microwave or pulse it with a laser, which gives it this pi half rotation around y. If you do this, this will always convert to 1. Now, when you make a measurement, for this state, you will get always a result 1, and for the other state, you will get 50% 0, 50% 1. So the key takeaway is the quantum state, even though when it's measured, it collapses probabilistically, is not the same as probability mixture. It is not the same having 50% something in the 0 or 50% in the 1 state, or having a system in a superposition of 0 and 1. Okay, and with this, there's also a concept of entanglement. What happens is that if you have an appropriate circuit, when you apply this circuit to 2 qubits, they can form a state which is they can form a state which they don't have their own states anymore. They form a shared state. So 2 qubits here are no longer have their own state. Now they are shared. They have this one shared. And what this means is, if you prepare such a state and now you measure qubit 1, the shared state has to collapse into 0, 0, which means that the qubit 2 also became 0 at that moment. If you instead, by measuring qubit 1, you get 1, you know that the whole thing must have collapsed into 1, 1. And therefore, the second qubit also must have collapsed to 1. This is the concept of entanglement. This is actually, what this means in practice is that you have very correlated states. In this case, perfectly correlated. If you get 0 on the first qubit, you know you will get 0 on the second, no matter if you measure right after or a lot later, you will get the same result, consistent with this. Okay, and the final note about qubits is that a physical realization of a qubit is not so important to us. So a physical realization of a qubit to a quantum computer is something like a type of transistor used in a classical computer. In a classical computer, you can use many different types of transistors, and logical circuits are going to be implemented just the same, even if a circuit is built with a MOSFET, JFET, BJT, or IGBT. The difference is they will have different performance characteristics. So MOSFET is good because it's switched it's capacitively voltage controlled, not current controlled. BJT is current controlled, not voltage controlled, which means that in a BJT circuit, you would have the processor, even though it has the same function, would heat up more, would have, then you have different things like switching speeds. Switching speeds go up and down. And so even though the logical operation would be exactly the same, we would have some performance differences. For quantum systems, for 2-level systems, it is pretty much the same. It is a very similar story. So there are many ways to realize a 2-level quantum system. One way is the superconducting circuits. A superconducting circuit is, the picture of that is what you saw in the intro to this talk on Meetup. And here is also a picture of the same thing. This is from the Quantum Devices Lab at ETH. And this on the right is the picture of the actual active element inside. The thing that kind of makes it work is exactly here, and it is called the Josephson junction. Again, the specifics are not so important because all the superconducting circuit, trapped ions, neutral atoms, quantum dots, they all form 2-level systems. The difference is how long they can keep their quantum properties, how much you have to cool them, how fast are the operations, and so on. But from our perspective of building a quantum algorithm, it is irrelevant. We are just happy they provide us with their gates and their hardware, and we just do what we want. Okay, so quantum computing. Onto quantum computing. What is the idea here? Well, what is first the difference? I'm sure all of you have seen these quantum diagrams, but what is the difference between this and that? Well, the difference is, pretty big. So A here, in a classical circuit, and A here gets inverted. So if here was 3.3 volts, here becomes 0, or 0 becomes 3.3 volts. And a quantum equivalent of a NOT gate is an X gate. But an X gate works differently. An X gate here overrides the state of this qubit. It doesn't here, A stays A. You just get a new bit here, essentially. But here, X gate overrides the qubit, that overrides the value that was here. And it's impossible to copy. And what these diagrams essentially show, they show how you apply operations in time. So this is the time axis. So you apply this operation first, then you apply this operation, and then this symbol means you measure. And in addition, because evolution in quantum mechanics is unitary, it must be reversible. And this means that the circuit must be built of reversible elements, which means, for instance, here, an AND gate, which destroys the information, because if it's 0, you do not know if this was 0, 0, 0, 1, or 1, 0. This cannot directly be implemented in the quantum computer. You need something like this. Okay, so now I talked about all these quantum gates. How do they work? Or what do they actually do? Well, a single qubit gate performs a half-circle rotation around the certain axis on the block sphere. So if we have a poly X gate, it performs a half-circle rotation around the X-axis on the block sphere. Now, this is a bit different demonstration to this one, but it will be here on our previous drawings. And you see 0 becomes 1, and by the same way 1 will become 0. This is why poly X gate is the equivalent of a NOT gate in classical computing. The poly Y, Z, and Hadamard gate do the same thing, except the axis of rotation is different. Here the axis of rotation is Y, here it's Z, and here is this weird one. But what Hadamard does is it converts this one into that one and that one back. But only being able to run single qubit gates is not really useful. We need to be able to make entanglements to build. We need at least two qubit gates, and one such gate is a CNOT gate. Now, the way a CNOT gate has a control and a target qubit. So the action is pretty simple. If a control qubit is 0, don't do anything. If a control qubit is 1, change the state of the target. Now, on the right is an example of a circuit which creates that entangled state that we saw in the entanglement example. So here, you apply the Hadamard gate on the first qubit, and then you make a CNOT gate on the both. And what this does is it creates this highly entangled state. And now, if you were to only measure this one, and you measure 0, you know that if you measure this one, and then at a later point in time, you would also get a 0. Or if you got 1, you would also get a 1. And now, this brings us finally to the general idea of quantum computation. What do we do with quantum computers? What we do is we take n qubits on the input and we put them in some initial state. Then we apply a unitary operation on them. This is some sort of a gate. This inside can consist of many, many different gates, but they're all unitary and they can all be abstracted away as one unitary. And then we measure every one of them, or perhaps a subset of them. The information about the problem at all times is essentially stored in the analog form, in the quantum state. The quantum state is not digital. It's somehow weird because before you measure, it has those two real numbers. Real numbers have infinite precision. They're not digital. But when you measure, it collapses into 0 or 1, which becomes digital. So quantum computers are somehow both analog and digital at the same time. It's a bit difficult to categorize them so simply. All right, so now, what is the idea behind this quantum algorithm? Well, the idea is as follows. Suppose we have a function or a problem we're trying to solve, and the solution to the problem is 0, 1. What we do is we initialize the state here on the left. In almost all algorithms, we initialize the state to be in equal superposition of 0, 0, 0, 1, 1, 0, and 1, 1. So these numbers are all the same. Here is a numeric example for demonstration. So 0, 25, 25, for every single one. Now, what does a quantum circuit or a quantum algorithm do? What a quantum algorithm does is it increases the probability, increases the amplitude in front of the solution. So if the solution is 0, 1, alpha 2 is going to increase. And because the state needs to have length 1, all the other ones will go down. So the way it does it in practice is by doing constructive and destructive interference. But from our perspective of this state vector, what it does here is demonstrated perhaps maybe even better on the numerical example down there. These equal superpositions after the quantum algorithm become such that the solution is much more likely to be measured. When you make a measurement, you're much more likely to measure this 0, 1, which is the solution to our problem. And that is the essence of the basic idea of quantum computations and quantum computers. Now, to do this, we of course need to simulate. We need to be able to implement functions on classical functions that we know of on a quantum computer. Now, the way this can be done is, suppose you have a function on a classical computer. This function can be expressed as some sort of a logic gate circuit, and every single classical circuit can be decomposed into a sequence of NOT and AND gates. For every one of those, for a NOT and an AND, for a NOT and an AND gate, there is an equivalent quantum gate, which for NOT is called the X, and for AND is called this thing, which is called the Toffoli gate. Now, this is special because it's a reversible AND. See, if you put in something here, A and B, you keep it. You don't destroy it. Here, you destroy it. Here, you don't destroy it. You still keep it, which means you can invert this operation. And the basic then procedure is you take a classical function, build a circuit, a classical circuit out of it, replace every element with its quantum equivalent, and you get this thing called C prime here. C prime then behaves, it has the X as an input, and it has an output. So these, in case these 3 qubits are input, and these two qubits are output. So this function would be, takes two, length 3 input and length 2 output. Now, this is then a stepping stone towards these two things. And these two things, on the left, this is called the bit oracle. On the right, this is called the phase oracle. It is perhaps a bit more complicated to explain all the details of this. But the point is, if you put here, here you put an X and an input, and here you have Y, and this is bitwise XOR f of X, which means that if you put here Y0, you would have X, and f of X as outputs, and that's it. So you have 3 qubit input and you have a 2 qubit output, which this is the bit oracle that we need. And on the right side, in the special case that the function has only 1 bit output, we can use this phase oracle, which is actually constructed from this one by changing the ancillas, these things down there, in such a way that if you give it X as an input, it will make minus X if this function was 1. If it was 0, then minus 1 to the power of 0 is still 1, so it's going to give you a positive phase. So this thing in front just gives you this phase, and this is why it's called a phase oracle. Now, these two things are perhaps a bit complicated to understand, but they are the things that we use in quantum algorithms to do something, because we have a classical function, and from this classical function, we build the bit and the phase oracle. And then we use those things in quantum algorithms to do something to solve a problem related to this function. So the first such algorithm is called the Deutsch-Jozsa algorithm. What it does is it solves an artificial problem with no known use case. The problem is as follows. Suppose you have a function, and I promised you, I give you a function, and I tell you, this function is either constant or balanced. Constant means for every, suppose function takes values from 1 to 1,000, and I tell you, constant means for every f of 1, f of 2, f of 3, f of 4, and so on, it is a constant value, a 1, or a constant 0. Or I give you a function that is balanced, which means that it has an equal number of arguments for which it is 1, and equal number of arguments for which it is 0. So for 1, it's 0. So f of 1 is 0, f of 2 is 1, f of 3 is 1 again, f of 4 is 0, and so on. The point is that the number of 1s and 0s must be equal. If you have such a function, you construct a phase oracle for it, and you initialize. So you initialize the qubits with this. So they are all in the ground state. When you put them when you put this Hadamard gate, you put them in the superposition between 0 and 1. You basically build this state. This is a case for only for a function that only takes 0, 1, 2, and 3. It's only 4 parameters, but it's illustrative of this, just with lower space. And what it does is it will amplify the probability that you get 0, 0 if f is constant. So in our case, in the case of Deutsch-Jozsa algorithm, with one call to this phase oracle, you will get 0, 0 on the output when you measure here, or in the case of many qubits, 0, 0, 0, 0, 0, and so on, only if the function that you gave me is constant. If the function that you gave me is balanced, then I can never measure 0, 0. And therefore, again, the way I use Deutsch-Jozsa algorithm, I initialize all my qubits into 0 state. I apply Hadamard gate to all of them. I give these qubits to the phase oracle, and then I do a Hadamard again, and I measure. Now, this is not expected to be apparently obvious why this would perform such a function. It's a consequence of running the mathematical analysis. But this is the algorithm, the first one to demonstrate that quantum computers can actually do something much faster than a classical computer, because once again, the classical computer would need to go through the entire key space. So if a function goes from 1 to 1000, for a classical computer to make sure that the function is constant, you would need to go through 500, so f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and it would have to call this function at least 500 times plus 1, 501 times, to make sure it went through half of the key space, and now it knows for certain the function is balanced, or constant, sorry. And the quantum computer can do this with only one call to the function, or this phase oracle. The next algorithm we're going to consider is called the Grover's algorithm. Grover's algorithm solves the problem of unstructured search on a set of n elements. So suppose you have a function, again, function from 1 to 1000 or from 1 to 10 million, or whatever, that has a marked element. So f of 671 is 1, and all other are 0. Now the problem is find 671. On a classical computer, the only way to do this would be to test f of 0, f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and eventually you would get to 671, and you would say, oh, I found it. A quantum computer implementing this circuit down there can do this in a square root of n steps. So if a function goes to 1000, a quantum computer can do it in 32 steps, whereas a classical computer has to do it, in the worst case, in 1000 steps. And again, looking at this circuit, it is not apparently obvious that that's what it does. And this is a very common thing with quantum circuits. This is why we don't have a lot of quantum algorithms, is because it is very, very difficult to find them and construct them. And yeah, when you run a mathematical analysis on this thing, you find out that what it does is it approaches the element, the correct solution, as you repeat R many, many times, it approaches the correct solution, but notice it never gets to it. It has this probability of it's close to it, but not exactly. This is why oftentimes for quantum algorithms, you need to check once you get the solution, once you get a result out of it, you need to then check this result on a classical computer. You actually, if a quantum algorithm tells you 671, you cannot just trust it. You have to go on a classical computer and test, is f of 671 indeed 1? And you say, yes, it is. It was correct. Or if it's not, you have to run it again. And if the algorithm is good, it will lead you to 671 pretty quickly. And the last algorithm of today is the Shor's algorithm. Now, Shor's algorithm is probably the most known of all the quantum algorithms, but it is also one of the most complicated to analyze, and we will not go into details here of how it works. But what we will do is say the following. The Shor's algorithm can be used to factor numbers indeed, but it's not actually a number factoring algorithm. Shor's algorithm is a period finding algorithm. So if you have a function and you want to find out what the period of this function is, you would use the Shor's algorithm. Now, the reason this is useful for factoring is due to number theory in mathematics. So you can construct a function whose period somehow depends on its factors. And then you use a quantum computer to find a period of this function. But looking at this slide here, a quantum looking at this slide, probability, you will see that it doesn't now just amplify one result like we had in the previous algorithms. Now it amplifies many results. And because a periodic function is periodic, and if R is a period, 2R is a period, 3R is a period, and so on. So you will fall into, when you measure the output of this Shor's period finding algorithm, you will find one of the periods, which means that once you do that, you need to use a classical computer to do some post-processing to figure out what the prime factors were. It doesn't directly give you prime factors. It is something that gives you a period of a function, which then you can use on a classical computer to find the factors of prime factors of a number. And this leads me to the final note about speed of quantum computers. In general, quantum computers have they're famous for being very fast, but this is often not the case. Quantum computers are actually much slower than classical computers in the sense that their operations are much slower. So a NOT gate on a classical computer has a switching speed in picosecond range, but an X gate on a quantum computer takes orders of magnitude longer, 2-3 orders of magnitude longer than this NOT gate. The advantage in a quantum computer is if you can find a quantum algorithm that minimizes the number of calls to the oracle, whether it be a bit oracle or a phase oracle. Once you have that, then you have an advantage. Because as we saw on the left, this is the Deutsch-Jozsa algorithm. It only needs one call to this phase oracle to get the solution. And on the other hand, a classic computer needs to do f of 0, f of 1, f of 2, f of 3, and so on to find the solution. So quantum computers are not just faster at everything. They're faster for a specific problem for which we have a known quantum algorithm. And this leads us to the cryptographic consequences of all that we discussed today. There are two general categories. First one is the consequences of the Shor's algorithm. The RSA cryptosystem relies on the fact that it's hard to factor numbers. Shor's algorithm can help you factor numbers gives you an exponential speedup in this case. In addition, discrete logarithm problem can also be efficiently solved with Shor's algorithm. And that problem is the basis of the Diffie-Hellman key exchange and the elliptic curve cryptography, which means that both of these cryptosystems are in danger of quantum computers. And the consequences of the Grover's algorithm is that because it has square root of n, it doesn't have an exponential speedup, but a square root of n means that it will have the key of a symmetric cipher. So if your symmetric cipher was 128 bits long, now with the Grover's algorithm, it's effectively 64 bits long. So, and in addition, we have the hash function collisions, which can be used or abused in mining. Now, why is this a problem? The reason this is a problem is this is, after all, an OWASP talk about web security. And we finally get to this point. In most modern web communication, it's protected by public key cryptography, either RSA or elliptic curves. And the way it's used is that RSA and elliptic curves are used to authenticate the server. So you as a client want to make sure that you're talking indeed to ubs.ch and not to some hacker pretending to be ubs.ch. And to make sure you're talking to the correct server, you use this RSA and the elliptic curve cryptography functions or cryptosystems. And then afterwards, usually, you perform a Diffie-Hellman key exchange. And afterwards, once you have the keys which you have transferred with this Diffie-Hellman, you use them in the symmetric cipher for communication. And this usually is AES. A quantum computer comes in and makes a problem because RSA elliptic curves no longer work. Diffie-Hellman no longer works. Symmetric ciphers are weakened. The solution there is to double the key space, the key length. The problem, of course, is you now have some performance penalty because of that, but it's not a deal breaker. but for RSA and elliptic curves and Diffie-Hellman, it is a deal breaker. So what do we do about that? Well, we implement something known as post-quantum cryptography. As I think, stressed, quantum computers are not universally faster at everything. They are faster for specific types of problems, which means there are also problems for which they are not very good, at least no better than classical computers. And we use those for post-quantum cryptography. So the problems that are just as hard on a quantum computer as on a classical computer and can be efficiently implemented in the classical computer. And what we need is the replacements for the public key cryptosystems, the RSA and the elliptic curves, and of course the Diffie-Hellman also doesn't work. And now there is a lot of effort in this areas. And NIST, the US NIST, National Institute of Science and Technology, has selected some algorithms to actually replace the above. So Crystal's Kyber is for public key encryption and key establishment. So it replaces RSA, elliptic curves, and Diffie-Hellman. And the bottom ones are replace digital signatures, because digital signatures also rely on public keys, public key cryptosystems. And the last word about current status of quantum computers. I've talked about how quantum computers work. I've talked about the danger that they represent. But at the moment, this danger is minimal. Current generation of computers, quantum computers, is something called noisy intermediate scale quantum computers. They have very significant scaling problems, and new breakthroughs are needed before we have actually usable quantum computers. It is not just about polishing something that we have a little bit. We need some breakthrough there for it to actually build a quantum computer that would be able to actually factor numbers. And a final point here is about quantum error correction. It is very likely, because these errors accumulate as the process runs, that quantum error correction is necessary to run any practical calculation on a quantum computer. But the problem is it introduces a very large number of helper qubits. So if your quantum computer has 1,000 qubits, but you need to use 800 of those to do error correction, or probably even worse, you have to use 950 of those to error correction, then you have a problem. Because, to be honest, probably even more. But you have a problem because you have actually a lot less usable qubits for your calculation. And then your quantum computer must be very, very big, have a lot of qubits to be able to do actual practical calculations. And we are, at this moment, very far away from that. Which leaves us finally with the conclusion. The conclusion is that quantum computers are an exciting technology with a lot of potential applications. They offer a speed up for only certain types of problems. What I didn't mention in the talk, I was focusing mainly on our kind of application with crypto systems, but quantum computers are going to be useful for different things, for simulating physical systems. That is what they were originally proposed for. That is probably what they're going to be the most useful for. But nonetheless, they pose a threat to current crypto systems. And because of that, and the fact that the process of standardizing things and implementing new ciphers takes a very long time, we need to essentially be ready. We need to act now. And if we now standardize post-quantum cryptographic systems, implement them in all major libraries and all major systems that rely on public key cryptography, we can sleep safe and sound. Because we know that if or when a quantum computer sufficiently large is built that can break these crypto systems, we can just turn those post-quantum cryptography systems on and seamlessly transition into the post-quantum era. And the quantum computers of today have still a long way to go. And with this completes our talk for today. Thank you very much for your attention.
Well, thanks a lot, Petar, for your insights. Very enlightening, actually. And are you already ready to take our questions from the listeners?
Yes, let's see.
Okay, you can imagine we have quite a lot of questions. They especially started dropping in when you came to more kind of practical aspects like strength of algorithms and what to use there. But let's start from the very beginning. We had one question from someone called Romy who asked that she would like if you could quickly explain again the difference or what it's about. It has with it the quantum state versus probability mixture. Looks like they're somehow related, but it didn't come out what exactly you meant with that.
Okay, it is a very complicated thing, I have to admit. I myself struggled somewhat to understand it when I first saw this. So suppose you have an atom, or suppose you have this staircase that I've showed here, and I tell you the following. I'm going to give you a staircase that looks like this, which is in a state described by this, this is the quantum state. And that is one option. The other option is I'm going to give you this, or I'm going to give you this. I'm going to give you this with 50% and this with 50%. When you perform a measurement on this, you will find out that if you just measure 0 and 1, so I already gave you a 1, so you just didn't know it. At this moment, you will just find out that I gave you a 1. Here, I already gave you a 0, you just didn't know it, so you just find out I gave you a 0. But here, the system will collapse into either 1 or a 0. This, if you do it like this is our first example, you see no difference. But what you can do is you can apply, I gave you this in a box. You don't know what it is, but what you do know is that you can apply these rotations around this block sphere. And if you do that, this state here, that was here, goes down, becomes a state 1. But here, it's this 0 and 1, they're not, this thing doesn't have a position on the sphere per se. It is 50% here, so it's like 2 branches. So I either gave you this, and then when you applied this operation, it became a plus here, this one, or I gave you this, and then it became this after the operation. And now when you perform this 0-1 measurement, in the first case, this will go down, which means you will always get a 1. In the second case, this went here. So we go 50%, I was here. Now I apply operation, I'm here. But now I still have 50% of going up and down. Or in another case, I'm 50% down there. Now I'm here, and I still have 50% of going up and down. So when I give you this, you will find out that you are 50% of the time you will measure 0, 50% of the time you will measure 1. Now, what is here also important maybe to say is that I don't give you just one such systems. I give you a box with either a quantum state or a probability mixture, and then I give you another one, and another one, and another one, and another one, as many as you want, and then you do these measurements. If my quantum state is up there, when you do this measurement, you will always get a 1. When you do this rotation and measurement, you always get a 1, always 1, 1, 1, 1. If I give you a box where I put either a 0 or I put either a 1 inside, then you will find out that 50% of the time it goes to 0 or 50% of the time it goes to 1. I hope I clarified it a little bit for you.
I believe so. Thanks a lot. Yeah. Then let's continue with a question from Alfred.
Mm-hmm.
You mentioned that, you explained quantum algorithms increase the probability of a solution.
Yes.
So you then also mentioned, how can we be sure that we found actually the right solution? I think you pointed at we have to verify with a classical computer. the question now is, are there other ways? For example, with the quantum world or something like that?
I do not. What you can do is you can measure the same thing over and over and over again. And you will eventually, if the solution is amplified, you will get this solution more and more often. But there is no guarantee that you will get, in general. In algorithms we saw here, it does. It tells you it's 100%, except the Grover's algorithm, sorry, it doesn't even tell you that. It brings you close to the solution, but then you still need to check it on a classical computer. I think for most algorithms this is the case, but not for all. For Deutsch-Jozsa, if you measure 0, 0, 0 at the output, then you know the function was a constant.
Okay, so you have kind of two types of algorithms. Some that you are sure they deliver the right solution, and others where you really have to check and actually also implement the algorithm twice, once for quantum and once for classical, basically.
Yes, correct, yes.
Okay, understood. So you also mentioned that, you said for many problems, quantum computers are actually a lot slower, but especially when it comes to, for example, breaking RSA, they have the potential to be faster if we would be able to, construct them enough qubits actually to search for the keys. The question that was posed now means, can you give us a number how much faster this actually is for RSA, for example?
The specific answer, the specific number, I do not have on the top of my head. I would have to search for it, but it is an exponential speed up. So here you can see the complexity, time complexity. As you can see, it's a complicated expression, but for a classical computer, this n is the number of bits. So if your number you're factoring has this many bits, this will give you, so it has, for instance, you're factoring 1024-bit number. This is 1024, and then the 1024 squared poly of logarithm of, so this poly means the polynomial with the logarithm of n. Now, logarithm of 1000 is 3. So this will give you 1024 squared times 3. That's the number of operations you need to do to factor a number. That is way, way less than you have to do to factor on a classical computer. On a classical computer, a factoring algorithm needs to go all the way from 0 to, there's the Eratosthenes sieve. I do not actually know on the top of my head what the complexity is, but it is much, much lower than this, because this is in the number of bits on the number, and the classical one is in the number itself. So if you're factoring a 1024-bit number, it's 2 to the 1024. That's the number you're factoring. And here you're only taking the 1024 bits as n, which is much exponentially faster.
Mm-hmm. Understood. Okay, thanks. Then we have a set of two questions actually that are a bit related to each other. On one hand, we had the question whether it would be feasible to implement quantum safe ciphers, or whether quantum safe ciphers need a lot more resources like CPU or memory, etc., than the classical ciphers, or if you can even use them on embedded systems, or if they are comparable to what we have today.
I unfortunately do not know the answer to this question. I'm sorry.
No worries. On the other hand, Christian asked us, well, first of all, he thanks you for the great talk. So just that I said it too. And he asked then, well, why is it not feasible to simulate such qubits on a classical computer, kind of simulate a quantum computer on a classical computer?
That's actually a very, very good question. And it comes back to, where were we? Building multi-states here. This gives you, so when you have, suppose here you have, if you have two qubits, you now have four complex numbers with which you describe this state. If you have 3 qubits, you have 8 complex numbers with which to describe this state. If you have 1,000 qubits, you would have 2 to the 1,000 real numbers minus some for the global phase and the normalization, but 2 to the 1,000 real numbers which you have to simulate. And 2 to the 1,000 is much more than, I do not know the numbers on top of my head, but I think much more than the number of atoms in the universe. So that's why.
Okay. So it has nothing to do actually with the fact that the alphas are real numbers per se. They do not need infinite precision or something like that. It's just the growth of how they sum up.
Well, I mean, I'm sure you will, with introducing like grainy numbers, which is what you have in classical computers. Of course, you will lose some precision, but that is not the main reason. You will just be somewhere close to the solution. That's still fine. The problem is the number of these parameters explodes that you will need to simulate.
Yeah. Jumping back to the quantum algorithms, safe encryption functions or cryptography functions, are there any of these ciphers you mentioned, are they already really used? How would you kind of think is the adoption rate of things like that?
I'm not the most, I do not unfortunately know that much about that. So I understand that NIST is standardizing them. It's in the process of being standardized. I know that some companies like Cloudflare are testing them, but I do not know the specific details of the adoption rate. I'm afraid I don't know.
Mm-hmm. Well, there's also the often heard claim that NSA can actually they already own quantum computers. Anything you can contribute to the rumors here, or?
Well, I would have to say that if that is the case, they must have the brightest engineers in the world, and they must have solved many, many problems that no one else has solved. And I somehow myself doubt that is the case, especially because people they hire have security clearance. So you cannot necessarily get anyone in, and I highly, highly doubt that's the case. Knowing what I know about the current state in research.
So basically, you say it would be a quantum leap forward. They would have
kind of.
without anybody noticing it.
Yeah. I somehow doubt it.
Yeah. Okay. By the way, you said that RSA is broken and our beloved Diffie-Hellman is broken. How is it with forward secrecy? So the perfect forward secrecy we now operate, is this included in that? Is it also broken, or does it still?
Well, I'm not an expert on this, so I don't want to say anything wrong. But as far as I understand, the perfect forward secrecy involves Diffie-Hellman, correct? Yes. So if you can, for instance, right now, as there are rumors NSA is doing, if you can log all the traffic going through a certain wire, and you memorize the thing you think is important, then yes, once the quantum computer exists, you can you first break RSA, and then you break Diffie-Hellman, and then you just read the data. That is true.
Cool. Thanks a lot. What's your take on the following? Is it likely that new quantum algorithms will be developed that can actually break what we thought is quantum safe? So basically, is there a proof that something is quantum safe or not?
Well, I'm not an expert in this, but I'm pretty sure the answer to that question is we cannot prove it. But remember, we cannot prove that classical computers cannot factor integers. It is unknown if that is possible. This is the P and P problem. It is perfectly possible that there exists an efficient prime number factoring algorithm for a classical computer. And if that turns out to be the case, then everything will be broken very soon. And classical computers, unlike quantum ones, we have very good classical computers that work very well. So the answer to this question, I'm pretty certain, is no, there is no proof, but it is assumed for good reasons, just like we assume for good reasons that we cannot factor prime numbers on a classical computer.
Mm-hmm. Yeah. Good idea. Next question. How do you actually write programs or functions for a quantum computer? I mean, do you need somehow to connect a classical computer to a quantum computer, or where is the program stored, or how does this work?
The way this works, and I think the best way to show this on the left picture here. So this is one realization of a quantum chip, of a quantum, of a multi-qubit system. And here, the way you control these qubits is by playing microwave frequency pulses to these different things. So these things are the coaxial connectors. This is the same thing, a bit more quality though, but the thing you used in your television sets when you had antennas. And here you connect to these things a function generator. And this function generator you control through a classical computer.
Okay, so you basically need a classical computer to operate a quantum computer as things stand today.
Yes,
yeah.
Yes.
Having said that, you mentioned that, it's still quite far away until we actually think that we can break in real world those crypto algorithms. But what kind of breakthroughs are actually still needed to make quantum computers feasible and usable also on a practical basis?
So there is this theorem or a statement from quantum error correction that says that if you have qubits, there is a graph that tells you how much better off you are when you implement quantum error correction. There is a certain line above which, if your qubit is better, the threshold, then you can just scale it up. Because the quantum error correction is going to take care of the errors. But if your qubits are above this line, adding quantum error correction actually adds more noise. We are currently, to the best of my knowledge, still right of that line. We are still above this threshold. And we still have, from what I know, a few orders of magnitude to reach the state where we are under the threshold. And this measurement is something called, it's just the quality of the qubit, how well it keeps the state.
Okay, thanks a lot. So to summarize things up, maybe that we learned a lot about quantum computers and their impact or potential impact on cryptography, but there's no need to panic right now. We still have time to fix our algorithms, get to the next stage, and make sure that we use quantum safe algorithms in classical computers.
Correct. Yes. We just need to act so that we are not surprised, but it is not alarming at the moment.
Great. Thank you very much, Peter, for all your explanation, for answering all our questions. I'm at the end of the list of all the questions, and I want to thank you again, and also the audience very much for being here and joining us for this talk. And if you loved it, and if you feel like threat modeling is also something you're into it, and you want to ensure that you do your threat modeling with reliable data, then consider joining us for our next talk on May 17th, where we have Tony, who's talking about these interesting topics. Thanks again for being here, and hopefully see you soon.
Yeah, thank you. Thanks for listening.